Okay, you guys, we need to get started. We've got a lot to cover today, so fasten your seatbelts. We're going to go very quickly through a lot of things for this week's class. So, announcements for this week. Experiment 3, we are doing Experiment 3 this week. I already warned you last week, read it very carefully because there's a lot to do and a lot you need to know. So make sure you read over that carefully. We're going to go through the steps of what you need to know today here in a minute. You'll have a quiz. Make sure, bring your calculator to lab this week. I can pretty much guarantee you will probably need it in lab this week, not only for the quiz, but other calculations that you need to make. So make sure you always have your calculator with you, not just this week, but every week bring your calculator with you. We're not going to let you use cell phones on quizzes. Your report for Experiment 1 is due this week in lab, so make sure when you come to lab this week you have it ready to go. Next week we'll be doing Experiment 4, and your Experiment 2 worksheets are due in the lab. For the Deaf Lab, so some of you guys worked in 3002 last week, the computer lab right next to the ducks. If you are having trouble with Chrome for the WebMO part, you can try, I've now found where Firefox is on those computers. So if you go under All Programs, there's an Email and Internet menu, and under there is where Firefox is. Okay? So if you need to finish your WebMO, and you need to use the Duck Lab, that's one way to use something besides Chrome, and you can try that out. So those worksheets will be due in lab next week, so make sure you finish those over the week. And then in 2 weeks, your Experiment 3 report will be due. So Experiment 3 is only a 1-week experiment, and in a couple weeks you're going to need to have that report ready to go. Okay. Another announcement I just wanted to make quickly, we are videotaping lab lecture. So I will put it up on Moodle as we will get it up as soon as we have it. We're kind of still working out a few kinks. So if there is a lab lecture that you know you're going to miss, hopefully we will have a video for you. But I would always make sure that you have someone else's notes too, just in case we have any technical difficulties getting it up. We have to go through YouTube to get it up on Moodle, and there's always a possibility, especially if you have 7:30 a.m. lab, maybe the video doesn't get up soon enough for you. So if you are depending on the video for lab lecture for a certain week, make sure you have someone else taking notes for you as well. Okay, so Experiment 3. Experiment 3 is a good lab because we start out smelling, it smells kind of like Thanksgiving or Christmas. We're going to start with nutmeg. So it smells like we're actually cooking in the lab. Although we're going to use so much, it's kind of really concentrated nutmeg smell. We're going to extract from that nutmeg something called trimeristin. And then we're going to use that trimeristin and we're going to make myristic acid from it. And so the myristic acid is your final product, but you will also isolate the trimeristin and characterize that along the way. So the trimeristin is a fat. So nutmeg, believe it or not, has fat in it, and it's about 20% or so of the nutmeg. And that kind of varies year to year on batches of nutmeg, but averages out to about 20% of the nutmeg is this fat. And that's calculated by mass. So one of the things when you are done with this experiment is you'll be figuring out how much of the trimeristin you were able to extract from the nutmeg. So trimeristin, if you recall from Gen Chem, if you saw any basic fatty acid chemistry, this is what trimeristin looks like. Getting final part of it here to make it an ester, getting the oxygen here. go. Better structures there. So we would call this a homo triester because all the chains are the same. We've got 3 esters here, and this backbone is glycerol. So it's a homo triester of glycerol. And it's really relatively, even though we do have the ester groups in here, so we've got a little bit of carbon oxygen, because of these long chains, it's really, for the most part, really low polarity. It's very non-polar compound. And so it's very soluble in ether. Or ethyl ether. We'll talk about all of the different names you can call ethyl ether, diethyl ether here in a little bit. It's not very soluble in methanol because methanol is such a polar solvent. And so we're going to use both of these solubility properties to help us isolate the trimeristin. So we'll extract it into the ether, and then we'll use the methanol to help precipitate it out and actually isolate the solid. And so this is our really important guide for the week, and then we will do a little bit of chemistry here to convert it over into the myristic acid. One thing I'm going to keep up here for a little bit and go through a couple things here. In your lab manual this week, you for experiment 3 do have a pre-lab write-up for experiment 3 in the lab manual. So page 38 and 39 shows an example pre-lab for experiment 3. First of all, what I want you to do is look at, after lab lecture, look at this pre-lab versus the Erlenmeyer example. They're a little bit different. So this is what I would call a more standard example of running a reaction and what the pre-lab should look like versus what we did for experiment 1, which really wasn't any true conversion of anything because we just deprotonated something and reprotonated it, okay? But this is actually a true conversion of our trimyristin into sodium myristate, and then we'll eventually make our myristic acid, okay? And so the mole table looks like, physical property table, looks like it should for each reaction from here on forward. And then also note, and we'll go into this in a little bit more detail here, what our flow diagram looks like. Remember, the flow diagram is showing the workup of the reaction. So it's not showing the reaction. That was what was shown on the first page. It's the workup of the reaction is what you're looking at in a flow diagram. So compare experiment 1 and experiment 3 because there are differences to them. And like I said, this is the more standard pre-lab for a true reaction sequence like we're going to do this week. So again, you get to have your pre-lab pretty much written for you. However, there are things to watch out for with this pre-lab. You need to draw in your own equipment. So we're going to use a reflux apparatus for the first time. We're going to use gravity filtration most likely for the first time unless you drew that previously. So make sure you get your new equipment drawn in your pre-lab. And then also be careful, the reference here is for the 2012 edition of the lab manual. We're using the 2013-2014 edition. So make sure you've got the correct reference for the lab manual as well, okay? And so before you come to lab this week, you need to have your pre-lab in your notebook. And from here on out, whenever you are starting a new experiment, before you come to lab, you need to have your pre-lab ready to go in your notebook, and that's going to be signed off while you're taking your quiz, okay? Now, what we're going to do is we're going to start with, in lab this week, we're going to start with isolating the trimyristin or extracting the trimyristin from the nutmeg. And like I said, we've got a really busy week this week, so you need to keep on top of all of the different steps you need to be doing, and as you're doing one step, be planning ahead for the next thing that you need to be doing. If you need to, I'd write an outline for yourself of all the steps because you don't want to have to spend tons of time just trying to find what you're supposed to be doing in your lab manual. There's a lot of words in there, so you need to be familiar with what all those words say before you come to lab. Now with this extraction, it's an example of isolating an organic product, meaning contains carbon, organic product here, from plant or animal material. And so we're doing this by extraction. And the trimeristin itself then is known as a natural product. Okay? And so this isolation of a compound from a plant or animal material is something that's fairly common in chemistry. And a lot of times this natural product then is used for some sort of, in the synthesis of a drug, or even tested for itself, by itself, to see if it would work as, have any efficacy as a pharmaceutical product. Now in this case, we're not going to go on and make any pharmaceutical products with our natural product, but the isolation of our trimeristin is an example of that. With this extraction, we're going to use what is called a solid liquid extraction, so it's a specific type. So in experiment 1, you used what was called a liquid-liquid extraction when you extracted your carboxylic acid away from your neutral compound. Now we're going to use a solid liquid extraction. So the only difference is this time we have a solid and a liquid instead of a liquid and a liquid, okay? And so instead of shaking in a separatory funnel, we're going to stir it in a flask. But we still, using the extraction, want to get our trimeristin out of our nutmeg, so we'll extract it out. Now, to isolate the actual solution of trimeristin, we're going to use filtration, specifically gravity filtration. And then we will isolate the trimeristin solution from the rest of the nutmeg that we don't want. And then with this, you're going to use something called fluted filter paper, which you may have already used if you had to do a hot filtration for experiment 1. But if not, we will show you in lab how to make fluted filter paper for your extraction, which we, beyond this week's lab, you will use many times throughout the rest of this semester and next semester for organic chemistry. During this extraction, we are going to use, our solvent is diethyl ether, okay? Which is also known as ethyl ether and also known as just plain ether. Now, it is a very volatile solvent, okay? And so it evaporates very quickly. It also, due to its volatility, is also a very flammable solvent. So we need to keep ether away from open heat sources. So you don't want a container open of ether right next to a hot plate. So make sure when you're doing this extraction and you're stirring the contents of your Erlenmeyer flask on your hot plate, that your hot plate part isn't on, just the stirrer is on, okay? So you do have to be really careful with diethyl ether because of its flammability and volatility. Also, because of its volatility and it evaporating very quickly, it's easy to extract trimeristin out of nutmeg and then have all your ether evaporate, and then you're basically back where you started again. You just got trimeristin out of the nutmeg, but you haven't really separated it, okay? So you need to cover you're going to cover your Erlenmeyer flask during the filtrate or during the extraction with saran wrap, and there's saran wrap in the labs if you haven't already found it. And then you also need to cover your funnel and Erlenmeyer flask during filtration. So both cases, you want to make sure everything is covered with plastic wrap, and do a really good job of covering it well with plastic wrap. If you don't do a good job during the filtration, it's going to mean that you have to do more extractions to get all your trimeristin out. So ideally, we're going to do 2 extractions and be able to stop there. But if you don't get all your trimeristin out of your nutmeg, then you need to do a 3rd one, because you need to make sure you have enough to keep going on with the experiment. Okay? And so you can tell if you don't have all your trimeristin out of your nutmeg, because it's like an off-white powdery solid, kind of almost looks like off-white flour, and then nutmeg, is like orangey red color. So it's really easy to see if you have all your trimeristin out or not, or if you have some residue stuck in it, okay? So after you do 2 of these extractions, if you have any questions, have your lab professor take a look at what you've got left, make sure you got all the trimeristin out, and hopefully if you don't, we can maybe do another rinse to get it out. If not, we may have to do another extraction. So be really diligent here, not with your ether. That will help you not have to do more extractions in the end, okay, which are more time consuming than covering with saran wrap. Another thing is you need to stir this pretty well to get the extraction to work, but make sure you attach your Erlenmeyer flask, clamp your Erlenmeyer flask to the ring stand. We don't want any Erlenmeyer flask walking off of the stir plate from stirring so rapidly but then fall off, okay? So be careful of that as well. And then, like I said, if you have any questions, make sure that you ask your lab professor. So there's a couple things that our extraction depends on, or solid liquid extractions in general depend on, and things that in designing this experiment we've tried to maximize for you so that you do have a good, successful solid liquid extraction. And a lot of these are the same for liquid-liquid extraction as well as solid liquid extraction. So the extraction depends on, first of all, solubility. So we've picked something for the solvent that is going to solubilize that trimeristin really well. And along with the solubility, also your volume that you use is appropriate to get all that trimeristin extracted out. So solubility is really, really key whenever you're doing an extraction. The number of times that you do the extraction. Let's try writing this again here. So, for example, we do the extraction 2 times with 30 milliliters of ether. Doing it twice, you will get more out than if you do it just once with 60 milliliters of ether. So even though we would total use the same volume of ether, multiple times is better than just once, okay? You want good contact. So we're using powdered nutmeg. We're not going to just use straight from the nut of the nutmeg to get better contact. Same with when you shake a separatory funnel, you're shaking the separatory funnel to improve contact of the layers so you get a better extraction. We want good stirring. And we've already talked about clamp that flask to the ring stand. And then what we're going to do after our extraction, so we'll have multiple ether layers, then you're going to combine your ether extracts into one, okay? And in doing that, what we're going to use a technique that we have used before for something called concentration of the ether extract. And so we've already talked about your trimericin's really soluble in the ether, that's why we're using it for the extraction. But then we gotta get that trimericin out. And so what we're going to do is we're going to concentrate the ether, or minimize how much ether we have. We need just a little bit to solubilize the other stuff we extracted out. And then we need to be able to crash it out of another solvent. And so we're going to use a simple distillation for this concentration. So we're going to get rid of some of the solvent. What you want is you still want about 15 milliliters of ether solution in the end. So we don't want all of the ether off, we're just going to take it down to about 15 milliliters. And in the labs we have 250 milliliter round bottom flasks with 15 milliliters of water in them. And so for the simple distillation, you're told to use your 250 milliliter round bottom flask. So before you start the distillation, before you even put anything in there, you can take your empty flask and mark with a Sharpie about where that 15 milliliter line is, so you have an idea when you're distilling how much you're taking it down to, because 15 milliliters in a 250 milliliter round bottom flask is kind of just like arbitrary when you're just looking at it, okay? But we do need to get enough ether off so that our trimericin isn't soluble anymore, but we don't want the other junk to come out as well, okay? And so that's why we're going to use this concentration. So another term that you could call this is a partial distillation. It's not a complete distillation. Now from your extraction, you're still going to have this nutmeg residue in your flask, and you're going to have filter paper with nutmeg in it as well, okay? In the reagent hoods, there's big containers that you're going to stick the filter paper into and the residue of the nutmeg. Whatever ends up drying up from the ether, you're going to put in these containers. Now make sure when you put it in the waste container, don't put any solvent or water or anything else in there. We just want the residue in there. In the hood, it'll eventually, the rest of the ether will dry off, and then we're just gonna, it's just nutmeg, so we're just gonna throw it away, but we need to get rid of the ether residue. So in that waste container, do not put any solvent, do not put any water to help rinse out the nutmeg. You're just going to put your filter paper with nutmeg in it and scrape out what nutmeg you can get out of your Erlenmeyer flasks after they dry, okay? Because once you are done with this distillation part, it's going to tell you basically use that same Erlenmeyer flask again that you had nutmeg in it, so we got to clean it out. And then we're going to do the precipitation of the trimericin. And so what was the other solvent that was important for trimericin that we talked about at the beginning? The methanol. So now we're going to use methanol because it's not soluble in methanol for this precipitation, okay? And so you'll have your residue from the distillation. Remember, you're keeping what's in the distillation pot, not the ether that was distilled over. And so you're going to have this trimericin residue with some other stuff in there. You're going to add the methanol, and hopefully what you get is a nice kind of milky white mixture that shows that there's a lot of solid in it. That solid is your trimeristin, okay? So make sure you have a milky white mixture before you go to filter. Don't just add the methanol and then go to filter and then, oh, I don't get very much, okay? Sometimes it takes a little bit of encouragement to get that trimeristin to crash out. So if you add the methanol and you don't have a milky white mixture right away, then what you want to do is try like a cold water bath with a little bit of ice, not super ice cold. Sometimes that helps encourage that trimeristin to come out of the methanol, okay? But you don't want to end up throwing away the filtrate that you didn't really get the trimeristin out of. The other thing to be really careful about is now we have multiple red cans with different solvents that kind of are spelled the same, okay? So we're going to have ethanol out this week because you need it for part 2. You're going to have ether out in red cans. You're going to have methanol out in red cans. So make sure when you are getting the solvent that you need, you grab the right one. So for the extraction, make sure you grab the ether. For this precipitation, make sure you grab the methanol. For the saponification that we'll go over here in a few minutes, make sure you grab the ethanol, okay? Be really careful about reading labels. Otherwise, when you get to this point, you may not be able to precipitate anything out if you have the wrong solvent too, okay? But make sure you have solid before you go to filter it. So you're going to precipitate it out. You're going to filter with vacuum filtration. Vacuum filtration is used when you want to keep the solid. Gravity filtration is used usually when you don't want to keep the solid. So we didn't want the nutmeg, so we use gravity filtration. Here we're going to use vacuum filtration. We want the solid, all right? Then we need to figure out what we are going to do with this trimeristin, okay? We need to keep going on with the trimeristin, but we need to know how much trimeristin we have. So we need to figure out a way to remedy that situation. So what we are going to do is, and actually with the precipitation, one more thing to keep it, I forgot to mention is, it tells you in your lab manual what solvent to rinse that solid with too. It's an ether methanol mixture, so make sure you read your lab manual for that. But now we've got this wet trimeristin. It's solid, not wet with water, but it's solvent wet. And we need to know how much we have. And so what we are going to do is first we're going to weigh all of the wet trimeristin that we were able to recover, okay? And you want, at this point, you want greater than or equal to at least a gram of trimeristin. If you don't have a gram of trimeristin at least when you go to weigh this, talk to your lab instructor right away, okay? Because we're going to have to remedy the situation. But first, we want to weigh our wet trimeristin. Then we're going to weigh a clean, dry beaker. And it needs to be clean and dry. So then this is part of why I told you last week, clean all your glassware. You're going to need all sorts of pieces of glassware. So one of your small beakers, make sure it's clean and dry and empty. Nothing else in it. Okay? And then you're going to weigh 0.1 to 0.2 grams of trimeristin into the beaker. Okay, if you're wavering right on that gram that you need, make sure, like, don't go for the 0.2 grams of trimeristin, aim for the 0.1 gram of trimeristin, okay, if you're really close to the amount that you need. And then you're going to set this aside, okay? And we need to let this dry. And then in open lab, you'll need to come back and get the weight of the beaker and the trimeristin, okay? So you need the weight of the dry trimeristin and beaker, and then you'll figure out how much dry trimeristin you have, okay? Then what we need to do is figure out the percent mass of this wet trimeristin was actually trimeristin, okay? And so you're going to take your, if you take your dry weight divided by your wet weight times 100%, you'll have what percentage of that mass was dry trimeristin. And so this is all happening after the fact, okay? So the only thing we are doing this week is weighing our clean, dry, empty beaker and weighing 0.1 to 0.2 grams of trimeristin into this beaker, and then we're just setting it aside to dry, okay? But once you get the weight of the dry trimeristin, then we've got to go through these calculations, all right? And so then you can use this to figure out what was the percent weight loss on drying, okay? So if you have the percent mass that was dry trimeristin, what percentage is going to be the percentage that was solvent? If you just take 100 minus this, right, you'll have the percentage that was solvent, okay? And so we need this percentage, or you could say percentage that was solvent or percent loss of weight that was lost by drying. Then we can figure out from this our extraction yield, okay? And so we need to know how much trimeristin we extracted originally from the nutmeg. So we're going to know all of our weight of our dry or our wet trimeristin. If we multiply it by this percentage, we'll get what that extraction yield was, how much dry trimeristin you got out of the nutmeg, all right? The other thing that you need is we need to know how much trimeristin we use in part 2. I'll talk in a minute about what is part 2. So that extraction yield and what you use in part 2 is not the same thing. Or this wet weight and how much you use in part 2 is not going to be the same thing. Because remember, you're going to take the wet weight, subtract this weight, and then you'll have how much you're carrying on to part 2 with. Okay, so you need to know how much you used. And then once you know how much you used, then you can calculate weight of dry trimeristin used in part 2. And so you'll take this percentage times how much wet trimeristin you used. You'll figure out how much dry trimeristin you actually used, all right? You need this number here because you need to figure out theoretical yield. So you're already going to do this for your pre-lab, but then once you actually do the reaction, you need to calculate it again in your experimental. So you need to know theoretical yield, and then from that you can calculate percent yield for part 2, for making the myristic acid, okay? So you need this number, the weight of the dry trimeristin, for your theoretical yield and your percent yield for part 2. And so, again, like I said, this weight, and this weight is what we get this week. All these calculations, though, need to go into your notebook before you turn in your report. All of this information is important for your report, all right? Okay, so now we've got our at least gram of trimeristin. Now we need to go on to part 2. So now we're going to take that fat and make a fatty acid out of it. And one thing too, once you have this, I'll talk about at the end of the lab period, once you have this weight of the dry trimeristin, don't throw this dry trimeristin away because you're still going to need it for something else at the end, okay? So it's used for this weight as well as something else for characterization. Okay, so part 2. I'm going to use what is called saponification, or it's hydrolysis of this naturally occurring fat. So it's also known as basic ester hydrolysis. This is something you will cover eventually in second semester. You will go through the chemistry of esters, and you will discuss ester hydrolysis at that point. And so, like I said, saponification is the basic hydrolysis of a naturally occurring fat. What you are doing when you are going through the saponification process is you're making a sodium salt of the fat. And so this is, or of the fatty acid too. Either way, going either direction. So if we've got like an example of our ester, we go through the saponification process, we're going to end up with this sodium salt of fatty acid, of a carboxylic acid. So we go from something that with this big long tail was nonpolar, was hydrophobic. Once you go through the hydrolysis step, you're now making it water soluble again. So kind of like we did in experiment 1 with our carboxylic acids, except for this time we've got this big old long chain on it, okay? So like, this is the same idea as what happens with soap. That's where saponification comes from, is soaps first were used, we've got plenty of man-made soaps, but first they were naturally occurring things that were then hydrolyzed with lye to make them soapy. So if we've got something that is really non-polar, and you put it in with the sodium salt of all these fatty acids here, we create what's called a micelle. And so this is how soap works to solubilize dirt, okay? We get all the chains that are like the dirt, and then they carry it away into the water that the dirt really doesn't like, all right? So when you are doing this reaction, you may see, it may look kind of frothy as it takes place because you're going from the triester to eventually making this sodium salt. You may see some bubbles that look kind of like soap bubbles, okay? And it's because it is, we basically are making a soap in this process. Now for that hydrolysis, we've got to be really careful of the stoichiometry that's involved. So we're taking this triester again, here's our trimyricin. We're going to heat it up at what is called reflux, and we'll talk here in a minute about what that means, with sodium hydroxide. Now, to take this triester and make it into one of these guys, how many equivalents do you think you need of the sodium hydroxide to make this happen? We need 3 equivalents, right? We need 1 sodium hydroxide for each of these esters. Okay, so this is where we got to start paying attention to our sodium, to our stoichiometry. We've got 1 trimyricin, 3 equivalents of NaOH. We're going to carry this out in a water ethanol mixture. So again, be careful, make sure you use the right solvent. And we'll talk here in a minute what this reflux means. And so then what we get out is we're going to get our glycerol. It's going to come off. And then we get 3 of our sodium salts here, so our soap. And again, this is going to be water soluble. This is our sodium myristate. This isn't what we want to isolate. We don't want something just soluble in water. We want the actual carboxylic acid. That's what we're trying to form, okay? And so, what we're going to do is take our sodium myristate So how many of these are we going to have for 1 trimerisin? Got 3 of those. We need to react it with HCl. How many? 3. And then once we react it with 3 HCl, then we will get the product that we want. That is what we want at the end, is this guy here. That's our myristic acid. Try and draw this guy a little bit better. And then we also get sodium chloride off as a byproduct. So then this is not water soluble. Okay. Then this is what we will crash out of the water and isolate as our crude myristic acid. This week, we need to get to the point that we have our crude myristic acid. Okay, you need to get to the point that you have this. We're going to filter this out of the water, and then we will also recrystallize this. If you have time, you definitely want to get through the recrystallization as well. But you, at the very least, want your crude myristic acid. Okay? If we had to, we could get to the point where we add the HCl to it, and then come back and filter. But a lot of times things don't even work so well there. Okay? So you really want to get to the point that you have your crude myristic acid filtered before you leave lab this week. So you got to really work hard to get to that point. If you don't get the recrystallization done this week, so we're going to recrystallize from methanol, and you need to follow the instructions for this very carefully. So there's very specific instructions in your lab manual because this myristic acid has a low melting point, so you need to follow the instructions very carefully. If you don't get to the point of recrystallization this week in lab, then you can either wait until next week. Experiment 4, for the most part, usually doesn't take the entire lab period, so you could recrystallize next week in lab if you can work quickly and efficiently in lab. Or you can come to open lab to do it. If you come to open lab, you have to have a buddy with you, and you have to let your lab prof know when you are coming and when you are there working in the lab. Okay? Because this is something beyond taking a melting point or collecting a weight. You need someone, a body there specifically with you, dressed appropriately for lab, and your lab prof needs to know that you are in there working. All right. So make those, whatever you choose to do, make sure if you're coming to open lab, make the appropriate arrangements. Okay. So in your textbook, and this is page 726, if you've got the 6th edition of McMurray, or page 810 if you've got the 7th edition. This is the basic mechanism for what is going on in the ester hydrolysis. So like I said, you will cover this in more detail in second semester, but just so you have an idea of what is happening, we've got the OH group from our sodium hydroxide, that's attacking our carbonyl of our, of our triester. We form what is called our tetrahedral intermediate once that occurs, okay? And then we have our electrons are flowing back to the carbon, and then we lose this OR group. And so we have our acid and this OR group. But then it typically wants to then deprotonate that carboxylic acid due to relative pKa's. So then we do, if we stop here, we're just going to still have the salt. We need to add acid to actually precipitate out the carboxylic acid that we want, okay? And so like I said, you will go through this in more detail in second semester in lecture, but I wanted you to make sure you were aware of the process that is involved. So for this hydrolysis reaction, we are going to use what is called a reflux for the reaction. And so what we are going to do is we're going to take advantage of the boiling point of the solvent so that we can have a constant temperature for our reaction. So the boiling point of a solvent stays constant. It's not going to change no matter how much heat is added. And so we're going to take advantage of this constant boiling point for this reaction. Now the thing that's important to this is we can't lose our solvent, okay? So with reflux, you've got the boiling of the solvent, but we also need condensing of the solvent so it doesn't go away. So keeping things at a constant temperature will only work as long as you've got solvent in there, all right? And so we are going to use this apparatus this week for the reflux. I would recommend, you can even put your stir hot plate under here, so then you don't need this iron ring to support the heating mantle. Just have your stir hot plate, heating mantle directly on your stir hot plate. Have stir bar in your reaction flask. You're going to very carefully but tightly clamp your reaction flask. Make sure it's clamped tightly because you need to lift this in and out of the heat. Then you're going to have your liebig condenser. Then this clamp is clamped loosely. It's just there for support. You want your reflux to be nice and vertical, okay? You don't want any flopping either direction. Just like with the simple distillation, you have water in on the bottom, water out on top. Do not put anything in the top of the reflux because then you would have a closed system, okay? So nothing goes on top here. Now this is the first time we have used our heating mantles. Our heating mantles get plugged into the ohmite, those variable voltage controllers that are on the side of your hood. Don't plug your heating mantle directly into the wall socket. It goes into the ohmite, okay? So make sure you do that. Otherwise things will heat up way too quickly for you, and you have to cool things down again, okay? Now you're doing a simple distillation earlier. You're going to have a condenser already hooked up. Keep that condenser hooked up because you're going to need it again for your reflux, all right? So don't take things apart and put things back together again that you need. That'll help save you time. Also with the simple distillation, ether has a relatively low boiling point, so if you start with really hot water during the simple distillation, that'll help that process go more quickly. So these are the type of things you need to think about for this week in lab to help things go more quickly and efficiently to get everything done that you need to get done. For the reflux time does not start until you've got boiling and condensing of solvent. And you want like a nice, like if you're cooking, a nice simmering boil. You don't want it out of control all the way up the condenser. You just want it boiling nicely, and then you want the condensing of the solvent. Once that is occurring, then you can start your 45-minute reflux time. So just turning on the heat isn't when 45 minutes starts. It starts when it's actually refluxing, okay? So you may have to turn up the heat a little bit to like 50, 60, 70 on the ohmite, and then turn it back down once you get it to a steady boil, okay? Whoops. So just be really careful with the reflux. You need to keep an eye on it. You're not just going to turn the heat on it and then walk away from it. You need to keep an eye on what's going on. And before you even start the heat, your lab professor is probably going to want to look at your apparatus because it's the first time you've set it up. Okay. Two more things I want to go over really quick. I know we're right at time to go, but I need you to know for characterization. Okay, so your trimyristin and myristic acid, you're in various ways you're going to get yields, right? So we've already talked about trimyristin. Myristic acid, once you isolate it from the recrystallization, let it dry, you will get the yield, okay? So we need yield of these guys. We also need the individual melting point of each of these, of trimyristin and myristic acid, okay? So that's why with the trimyristin, with that extra sample that you have set aside, besides getting the weight of it once it's dry, use it for the melting point. So you need a melting point of trimyristin, melting point of myristic acid. Then we need to prove that these are not the same thing. So using what we know about melting points, what would you use to prove they are not the same thing? You want to prove that you actually converted trimyristin into myristic acid. Of what? Of these guys, right? And you should see the opposite of what you wanted for experiment 1, right? You should now see the lowering of the temperature, the broadening of the temperature range to prove that they are different, okay? So you need individual melting points and you need to prove that they are different, as well as all the yield information and then the calculations that we've already gone through, okay? Questions you guys have? Okay. Have a good week in lab.